As we are in the chapter of dynamics, we are really caring about a very important physical force that affects any moving object or even any object that is stand still, which is the force of friction. Any object moving on a certain surface or even sitting on a certain surface is being affected by friction. When you hold a box in your hand and put it in the table, the reason why this box is not moving anywhere because of the friction between the surface of the box and the surface of the table. If there is no friction, then any object moving will keep moving, and any object you try to set it in a certain surface will be able to keep moving it forever without stopping anywhere. Friction have many types. There is a static friction, there is a dynamic friction. Friction is affecting any moving or sitting object as we mentioned. So we start with the static friction. Static friction is the force exerted on an object at rest that prevents that object from sliding. When you put a table on a flat surface or even inclined surface, what keeps that table stand still is the force of friction. This table will keep standing on that object at rest until a force greater than the force of friction and force of gravity is applied toward that object to keep it moving in a certain direction. To explain the concept of static friction, we have here a table and there's a person trying to push this table, and we have the Cartesian as our standard coordinates. To the right is positive, going up is positive as well. The displacement velocity is 0 in this case. So we have the force applied by this person that is happening at an angle. As you know from vectors, this force has components in the x direction and in the y direction affecting on the object that we're talking about over here, which is the table. As you're trying to move the object to the right, as we saw previously in our examples, there is a static or there is a friction force affecting in the opposite direction of the force. This force in this case is called the force of static friction. Now this person came to the table is sitting on the surface doing nothing. This person applied a force, but the moment he applied the force gradually, the table didn't move until a certain point, which you know from your experience, you need to apply a little force, then the table will start moving. That period between you start to apply the force and before the moment the table start to move, you are applying a force, but the table is going nowhere. In this case, you are trying to apply enough force that is equal to the friction force applied on that table. This force that is resisting your force applied on the table is called the static friction force. So in the x direction, the total force on the x-axis equals 0, which means that the force applied in the x direction, the x component of the force applied, must be balanced by another force. This force is the static friction force, or the force of static friction. We, for abbreviation purposes, we say it is F directional of small f static. The equation for the net force acting on the disk in the x direction before the moment the disk moved. So we're talking static friction in this case. So let's confirm that point. You apply a force, the table didn't move anywhere. That's what we're talking about here. Before the moment the table start to move, which could be dynamic friction. It's another story that we will talk about as moving forward. So the F net in the x direction equals the applied force in the x direction plus the static force in the x direction. We know that the applied force in the x direction total is 0 because the table didn't move anywhere. But the applied force is of the x direction is F applied cosine the theta to get the x component, plus the F static is going in the left direction on the x-axis. There is no components into it other than the x component. As the static friction force applied to the left, and we have the convention that anything moving to the right or any force to the right is a positive force, any force to the left is a negative force. We can see here by rearranging the equation, this static force equals minus the applied force cosine theta. So the direction of static force is on the left or to the left compared to the applied force acting on the disk. Now let's take an example on the static friction on a horizontal surface only. So we have a magnitude of the applied force, as we see in the figure over here, of 165 newtons. The theta of the applied force is 30 degrees. So you are applying a force with 30 degrees reference to the x-axis. If the disk remains stationary, so the disk still static, didn't move, calculate the force of static friction acting on the disk. We draw the forces on the disk in a style of 3-by diagram, and we list down the givens and required. What is given? F applied is 165 newtons, and the theta of the force is 30 degrees. Now what he needs, the force of static friction, F of small f static. So we start with a 3-by diagram. You have the table here. You have applied force here with 30-degree angle. The applied force here can be split down to F applied X and F applied Y. And the static friction force would be going in the opposite direction of the applied force horizontal. And you have the gravitational force and the normal force. These are always there in the 3-by diagram as long as the object is having a mass. We draw a forces schematic or vector schematic. We have F applied X and we have F static going to the left. The F net would be 0 because in this case the table didn't move. The F applied X equals the F friction static. You have as well on the Y direction, the F net Y is 0. The table didn't move up and down or right and left. F normal up, F gravitational down. The F applied Y would be this way, but F net Y is 0 anyway. So we write the equation for the net force on the disk in both directions. The X direction, F net X equals F applied X plus the F static, and the F net X would be 0, which equals the F applied X. That's what we will calculate, which is F applied cosine 30 plus the F friction. But by going only with rearranging those parameters, F static would be minus the F applied X, and F applied X is F applied by cosine theta. F applied is 165 newtons as given in the question, multiplied by cosine 30. That would give you minus 143 newtons. In the Y direction, F net Y is 0, which is the F normal plus the F applied Y plus the FG. And in this case of the problem, the calculation of the Y direction is not required, so don't worry about it. There is a value into it, but don't worry about it in this case.